In this video, we are going to look at various types of distributions. We're going to use R. It's a statistical package, a standard statistical package that's open source. So you should be able to run the script that we have here and duplicate everything that I do today. I'm going to just briefly show you how this works. So first I opened up a script. I went to File, Open Script, and then chose this distribution example. Now, in order to run this particular program, we need to add a library. There's the basic R package, but some functions require additional libraries, and this one requires moments. And moments are the kurtosis, skewness, variance, mean. Those are all moments. And to get that, you would go up to Packages and install a package, and you would choose a particular place. USA, Oregon is where you're going to get it from, and then it will give you a list of packages. You'll go down and find moments right there, and select that, and it will install the package. Then when you run the program, you need to call it up, and you need to tell it to go to library and pick moments. You can also, as you see, I have in here, I have made a command, install packages with moments. You can just highlight that area and do Control R. Control R runs a program, and you can do that and also go through those steps. So you can either do it this way with install.packages moments, or you can go up and choose the menu packages and install it that way. You only have to install it once. It's then on your computer, and you don't have to do it again. But each time you do use it, you have to tell R you want to add this library. And so we come here. Now you can to run each line, or to run anything, you do Control R. And so now this just ran this line, library moments, and it entered the program. All right, now you can highlight various things and hit Control R to run multiple lines, but we're just going to do one line at a time. So I'm just going to continuously hit Control R as we do things. So the first thing that we're going to do is look at a uniform distribution. In a uniform distribution, as in any normal distribution, all values have, or all observations have an equal probability of being selected. The characteristics of a random distribution is, it's called independent and identical distribution, IID. And that means that everybody has an equal chance of being selected. In this case of a uniform distribution, in addition to having an equal chance of being selected, the probability for any one observation being selected is the same. In other words, there are the same number of observations at each point along the line. So let's see what we're talking about here. Let me, I'm going to first run I've just now set into the variable unif. I've created a density function. So here we're going to print the first 10 observations. So we randomly sampled 10,000 and numbers from -3 to +3, and these are the first 10 numbers that were selected in this random distribution. we can plot a little graph of this by hitting Control-R on histogram. And you can see it's a very flat graph that goes across here. So this is one type of distribution. If we look at some of the, well, let's continue on here. Let's look at the mean of this. The mean comes up here. The mean is 0.0054. You can see that this distribution goes from -3 to +3. The mean is pretty close to 0, which it looks like it would be. The median, that is 50% of values are above and 50% are below the value 0.0189825. So the standard deviation is 1.72, so we've come out 1.72 plus or minus 1.72 would be there. But that's the average deviation. Now, if you think about it, the average deviation from the mean at 1.72, now 1.5 would be the midpoint. Standard deviation is actually a little wider than that halfway point to get at the average deviation. We'll talk about calculating standard deviation a little later. Skewness. Now, skewness is 0 if the data are symmetrical. And it's minus 0.019 is pretty close to 0. So the data are symmetrical around 0. A +1 would mean that positively skewed, there'd be a tail going out this end, and most of the values would be piled up on the left. Left skewed, points would be piled on the right with the tail going off to the left. But this has a skewness of 0. Kurtosis. Now, in R, kurtosis uses the original moments formula from just the history of statistics. And what people usually do is subtract 3. If you're the kurtosis of a normal distribution is 3, and it refers to the peakedness of this distribution. And we can see here that it's a -1, so it's saying our distribution doesn't have a peak. It's flat, and this -1 is indicating it's flatter than a normal distribution. A normal distribution would have, which is this nice symmetrical bell-shaped curve, has a peak near 0. This is flat, and so it gives a kurtosis of -1. Here we can look at percentiles. We have the 2.5% and 97.5%. That's like equivalent to the 95% confidence intervals. So there's 2.5% is shared at each tail. And we get numbers very close to our limit of plus and minus 3. Notice that 25% is at the halfway point between 0. 0 is the midpoint. The halfway point is 25%. 0 is around a number close to 0 is around the 50th percent. That's the same as the median. And 1.489% is pretty close to halfway between 0 and 3. So these percentages say that about 25% of the observations are at the left here, 25% between the median and this area, then the next block and the next block. So it's evenly distributed across there. I've done the 16 and 84% because in a normal distribution, half the observations would fall in here. That's just for information. Okay, now let's look at the normal distribution. So we're down here. We're going to look at the normal distribution. We're going to sample 10,000 observations. We're not going to give any parameters, so it's to plus and minus infinity with 0 as a mean. And when you don't specify anything in this random normalization, you get a random distribution with a mean of 0 and a standard deviation of 1. And here are the first observations, the first 10 observations from our list. And so you get an idea what the values look like. And then here's the plot. Notice this is a pretty different looking plot. It has a nice symmetrical nature to it, a little peak at the center. Again, all observations have an equal probability, all numbers down here have an equal probability of being sampled. But some of the numbers, like -2, there are more -2s than -4. So you might have one person out here. They have the same chance of being selected as one in here. It's just that there are more -2s. There are a lot more zeros than there are -2s. And there's, about the same number of 2s as -2s. But all observations have an equal number of equal chance. They're independent and identical chance of being selected. It's just there's more of them when the number is closer to 0. Now the mean is again close to 0, -0.1. The median, similarly, mean and median very close to each other. Standard deviation, as I said, we're sampling from a distribution with a mean of 0 and a standard deviation of 1, so it comes up 0.99. Again, this is a random sample. It's not always going to come up with a mean of 0 and a standard deviation of 1. We're just sampling from an infinite population that has those characteristics, and we come pretty close. Skewness is close to 0 because there's no bias to the peak at one end or the other. There's no specific tail shooting off to the right or the left. Kurtosis, remember we're subtracting the kurtosis, we're subtracting 3 from the main kurtosis value, and we see that it's 0. So the normal distribution has a kurtosis of 0. And the quantities here are 1.48. 1.5. Again, that's actually pretty close to the other one. All right, let's look at a log normal distribution. So this is going to look a little different. Here are the first 10 values. And let's look at the histogram of this. Now, this, you can see, is a very different distribution. Most of the numbers are piled up near 0, and they tail off to the right. Our mean on this one is 1.6, way down here. Our median is 1.01. Now notice those are pretty different. That's because these values that are off to the right are waiting on the mean to drag it down, whereas 50% of the values are 1 or less. The standard deviation is 2. Notice that if we add 2 to our mean or subtract 2 from our mean, we get out into this impossible area. So this is where you have to be a little careful when you have distributions. This is why we're going through this exercise of looking at distributions. Sometimes you can't just assume that a mean plus or minus 2 standard deviations gets 95% of the values. Skewness is 12. Remember, skewness was 0 in the others, so this is a giant number. Kurtosis is really high. This is a very high peak. It's a very high peak, a very high skew. This is what this kind of curve looks like, as opposed to 0 and 0 for a normal distribution. And we get our quartiles. And it comes out giving us these negative numbers, which I'm not exactly sure why it looks like this. But on 0 and these numbers like this are just all crammed into this one little space. All right. Those are 3 different types of distributions that will carry on our conversation as to skewness, kurtosis, variance or standard deviation, and the mean.